So we're going to go over some of the notes from Newton's law of gravitation. So first of all, we're going to start with something we already know, that every object exerts an equal and opposite force on another object during an interaction. What we haven't talked much about is that every particle in the universe attracts every other particle in the universe. It's not just the Earth attracting things. This gravitational force is dependent on three variables. One is the mass of object A, the other is the mass of object B, and then also important is the distance that separates their centers. That center-to-center distance is this denominator r. That r is squared, which means that a small increase in r is a big decrease in the force. The fourth letter in this equation is the capital G. This is known as the gravitational constant. It basically just makes this equation work. The value of G is very, very small, 6.67 times 10 to the negative 11. And the units of G are newtons times meters squared per kilogram squared. Now those crazy units are there just so that this equation works, because gravitational force is a force, of course, it's measured in newtons. So this side also has to be measured in newtons. But as is, without G, we have kilograms squared over meters squared, and that's not a newton. So G has two jobs. It corrects the number, and it corrects the units. So most of the time we're going to focus on an interaction between two objects. But for example, we were interested in calculating the net force on the Earth due to both the moon and the sun. And then we would just use regular old vector addition, where the net force on object A equals the sum of the forces due to all the other objects that we're interested in. And we would just use vector addition, x components, y components, that kind of stuff. One of the very common scenarios we'll be looking at is orbital systems, and one type of an orbital system is a circular orbit. So this is a big if. So just to be clear before we move on, the derivation we're about to go through only is relevant if they have an object that's in orbit around a large object. For a satellite, the centripetal force is the gravitational force. And so as that object, little m, travels around in a circle, it experiences a force that causes it to accelerate at v squared over r. And the gravitational force is the centripetal force. So the mass of the satellite cancels out. Just like when we're dealing with free fall on Earth, the mass of the object doing the free falling doesn't matter. Just the mass of the Earth matters. And so we end up with this expression for speed. Now, I don't have it here, but write it in, just put a note on your packet. This equation is the speed of a satellite in a circular orbit around an object of mass big M. So that's the only time this is useful. Circular orbit, satellite speed, okay? This is a pretty equation, and sometimes people start just throwing it around when it's not appropriate. This next one is more general. To figure out the acceleration of an object in a gravitational field, we can just say F equals ma. So really what we're doing here is we're figuring out the free fall acceleration of little m. So yet again, the m's cancel out. And so we get this expression, a equals gm over r squared. So this is the acceleration of little m when it's in free fall due to big M. Okay, moving on to page 2 in your notes. So let's say we plug in specifically the mass and radius of the Earth into this equation. These two numbers are handy to have. You don't need to memorize them, but it might be worth it just so you don't have to look them up every time. The mass of the Earth is 5.98 times 10 to the 24th kilograms. The radius of the Earth is 6.37 times 10 to the 6th meters. If we plug these values in, we would come up with an acceleration of about 9.83, which is not what we use. We use 9.8 or 9.81. And the reason why is that the radius of the Earth is not a number that can be really pinned down. The Earth is not a sphere. It's called an oblate spheroid. It's slightly flattened from pole to pole. The equatorial radius is much bigger than the polar radius. So this value, if you were to plug it in, is the average radius, and that's why we get a slightly different value. Okay, in all of these equations, the r is the center-to-center distance. Sometimes, instead of being given the center-to-center distance explicitly, instead we'll be given the altitude. The altitude is the distance from the surface of a planet to a satellite. So if I'm going to use any of the equations we've talked about so far, to calculate the center-to-center distance, we would add the radius of the planet plus the altitude. Now, if you start to actually dig inside a planet, then things get kind of crazy because the mass of the planet outside, okay, so imagine that you're on the surface of this planet, you start to dig, you get to this position of this dotted line. Then you are interested in figuring out what gravitational force you experience. Well, obviously, as you get closer and closer to the center, this R gets smaller and smaller, so Fg goes up. However, as you get closer and closer to the center, you also have mass pulling you in every direction. Since the, let's see if I can write on this. Since the mass of this piece here, oh my gosh, it's supposed to be an M equals the density times the volume, where this is rho, it's the density, and since that means that M equals rho times 4/3, oh my gosh, pi r cubed. If we take this value and we plug it in here for the mass of the shaded area, you see that the r squares cancel out. And what am I missing here? Yes. And so it actually, inside the planet, the gravitational force is directly proportional to r instead of inversely proportional. Once you get to the outer edge of the planet, then the gravitational field drops off at r squared. Okay, moving on to the next page, gravitational fields. So we need two objects to have a gravitational force, but we only need one object to have a gravitational field. A gravitational field is essentially a way of communicating the force an object would exert if it were to act on another object. So imagine like a black hole in deep space. It's very massive. It's very strong gravitational field, but unless there's another object that wanders into it, it's not exerting a strong force on any object. When we were representing a gravitational field, we use what are called field lines, which are just radial lines that point towards the object. Since any object that enters this field will fall towards it, we have the arrows that point towards the center of the object. The gravitational field strength is calculated by thinking about the force that this object would exert on an object that enters the field divided by the mass of that object that enters the field. And so, in a more simple sense, it's Fg over m. This should look familiar. This is just our equation for weight, Fg equals mg. So what we're looking for here is an expression that describes this value of g. Well, since gravitational force is gmm over r squared, then again we'll see the mass of the object that's experiencing the field cancel out. So this expression, gm over r squared, can be used in any situation to describe the force per unit mass exerted by an object. As you, sitting in your chair right now, are taking these notes, you are experiencing a gravitational field strength of about 9.8 newtons per kilogram due to the Earth. This, if you notice from page 1, is the same expression as the acceleration due to gravity. However, right now you are not accelerating at 9.8 meters per second squared. So gravitational field strength and acceleration have the same equation, but they aren't the same thing. Finally, if you know the gravitational field strength and you want to calculate the gravitational force, you would just do gravitational force equals mass times gravitational field strength. All right, that is it for now.